is the portion of the processed radiograph that's going to appear dark or black. And remember, what causes that on an image is when that X-ray goes through without interaction and it just hits the film directly. That'll make it black. Then radiopaque are the portion of the processed radiograph that appears white. And then we've got lots of grays in between, as we know, and that we'll talk about how that's dependent upon the subject characteristics. So structures that appear white on film are very dense, such as bone, amalgam, things like that, and they resist the passage of all of those, or not all of those X-rays, but they resist the passage of X-rays at differing levels. All right. So to have a diagnostic radiograph, we must have proper density and contrast. We want to have sharp outlines. We don't want it to be blurry. And we also don't want a lot of distortion. We don't want things all wonky and stretched out really long or really short. So we want things to be the same shape and size as they appear, or as close as we're able to duplicate that. So the visual characteristics will start off with our density and contrast. So density is the overall darkness or blackness on a radiograph, and the influencing factors for density, as we remember from the last couple chapters, are KVP. But if we increase KVP, we increase density as well because we're giving those X-rays more energy, but it's not the controlling factor. Milliamp, time, those are going to be your controlling factors for density. So if I'm really wanting to change my density on an image, I'm going to mess with MA and time, not KVP. And then subject thickness is going to be an influencing factor as well to the density on my film. The difference in degrees of blackness between adjacent areas is how contrast is defined. So a lot of people will get confused between density and contrast, but contrast is just how those differing shades look next to one another. So we talked about low contrast is lots of grays, so there's lots of differing shades, and high contrast, there's not, it's just black and white. And we know that KVP is the controlling factor for contrast, and it has an inverse relationship with contrast. So that means high contrast, again, black and white. Low contrast, many shades of gray. A compromise between these is what's preferred in dentistry, but like I said, many general dentists like that high contrast for decay detection, and periodontists tend to lean more on the low contrast end because they like to see more differing shades. Contrast can be determined by film contrast. You guys aren't probably going to work with film, but the qualities of film and how film is processed, we're going to learn about processing today and some of the things that can affect our film contrast in that processing process. Subject contrast are the characteristics of the subject that we're actually imaging that influence that contrast. So how thick a person is, how dense their tissues are, all of those things are going to affect the contrast of the final image. Scales of contrast we've touched on too. So short scale is high contrast, long scale is low contrast, and we know that low KVP is going to give me high contrast and high KVP is going to give me long contrast. So this is all just kind of review. These are the things we haven't talked a lot about, the geometric characteristics. The geometric characteristics we're going to cover are sharpness, magnification, and distortion. Sharpness is when I was talking to you guys about like pixels versus the size of the silver halide crystals, I compared it to a television. And that's what I always think of when I think about sharpness is, you know, the more detail you can give me, the more sharp the image is going to be. So the more pixels you have, or the smaller the crystals, the sharpness is going to improve. So the capability of an X-ray receptor to reproduce distinct outlines of an object is how we can improve our sharpness. So there's always going to be some lack of image sharpness present in every radiograph. There's no way to make it exact. And that fuzziness around the outside of the image is called penumbra. So we're going to talk about the things that affect penumbra, and will give you more of that fuzziness or less. And of course, we want to shoot for less. We want it to be as sharp and crisp as we possibly can. Sharpness can also be termed detail, resolution, or definition. You might hear somebody use those terms when they're referring to image sharpness. If you look at this image on penumbra, this is in your book, and there's a whole chart on geometric characteristics at the top of page 77 that kind of tells you the influencing factors and then the effects of those factors. So that's kind of a good reference to kind of wrap your brain around some of this. So if you look at the image that I have on the screen, remember I've always talked about that anode target and how there's a focal spot right kind of in the middle of that target. We want our x-rays to be super hyper focused on that tiny focal spot, because if those electrons come in and hit that small focal spot, then they don't fan out as much or diverge as much. And the more divergence we have, the more penumbra we have. So if you look at the image on the left, you can see there's a large focal spot. And if you look at the final image down below, you can see all of that fuzziness outside of the tooth. And that's what happens when those electrons come over and they create X-ray photons, and then those photons have more room to kind of go all willy-nilly and give you that unclear image. So if we have a small focal spot, it kind of keeps them hyper-focused and they come out and we don't have as much of that penumbra. So the focal spot size is one thing that affects sharpness. We want it to be small. Film composition, again, is the size of our crystals. So the bigger the crystal, the faster the film, but the lower the sharpness or resolution. In digital, it's going to be the number of pixels. So the more pixels we have, the sharper the image. The other thing that can affect sharpness, obviously, if you think about it, is movement. And that can be movement by your patient. That can be film, the film moving while you're trying to take it. Maybe their tongue hits it and it's in motion when you're actually snapping the x-ray. Or the tube head. We want to be very cognizant of that. Once we place our PID up to the XCP, we want to make sure that it's not bouncing around. You want to kind of make sure that you kind of steady it before you go out to hit that exposure button, because movement can cause a lack of sharpness as well. Magnification. So magnification is what's going to result from those divergent X-rays from that focal spot. There are a couple things that can influence this. The longer the PID, that's why we like to use a 16-inch PID. So the longer the PID, which would be my target to receptor distance, will result in less image magnification, because it is filtering out those long, lazy X-rays. So you've got more filtration, and by the time it gets out that long PID, you're focusing down to using just the middle of that beam. So you don't have as many of those divergent X-rays by using a long PID. Then the other thing that is important, but with human anatomy is not always possible, and that is the object to receptor distance. In an ideal perfect world, we would love for our film or our sensor or our PSP plate to be as close to the tooth that we're imaging as possible. However, when we're working with XCP, I'm going to show you guys in Dexter's mouth, with a lot of our periapicals, you have to almost go to the middle of the mouth in order to get it positioned parallel to the tooth. Due to the structure, the bone structure, the palate, all of those things, there are many times that when we're using paralleling technique, you cannot be right up next to against the tooth. So that is where, with paralleling, we especially want to be using a 16-inch PID, because that's going to kind of compensate for some of that object to receptor distance magnification. And in this image, which is seen on page 78 at the top, you see the anode, you can see the divergent paths of those X-ray beams. The object would be our tooth. And you can see how if I moved that piece of film farther away from that object, it would allow those X-ray beams to diverge even more before it actually hit the film. So the farther you move away, the more magnification is going to result from that. But if I have a long PID, it's going to cut off a lot of those divergent X-rays before they hit my object. So that's where we can kind of compensate for some of the magnification caused by the tooth to film distance that we have to have. Okay, now we're going to talk about distortion. This is different than magnification. Distortion is a variation in size and shape of the object being radiographed. So we will see some magnification, but we're seeing magnification in different parts of the same object. And this is caused by improper beam alignment or angulation of our X-ray beam. So the influencing factors here are the object to film alignment. So we were talking about this with bite wings. If I don't have my image receptor aligned parallel with my teeth, then I am not going to, I'll probably have overlap. So it's going to be important always, whether you're worrying about distortion or overlap or whatever it may be, the most important thing is to have that object and film aligned, parallel. So the X-ray beam angulation must be directed like perpendicular to the tooth. If you're wanting open contacts, it's got to be perpendicular to those embrasure spaces between your teeth. If you're wanting a tooth to be visualized on the final image without distortion, you want it to be parallel and perpendicular. And the next slide shows you kind of how that can distort. So this is where we would, if we had to have a film positioned in this way, in order to avoid distortion, this is where we would have to use the bisecting technique, where we would have to kind of find a middle ground between the angle of the angle that is created by the film and the tooth, the long axis of the tooth. You have to kind of divide that in half and now aim your X-ray beam at that to decrease some of that distortion. Don't worry about that because we're going to have a whole section on bisecting, but I'm just showing you when you look at this tooth with this film laying at an angle as it is here, that black line that shows exactly how much of the tooth would be, how the tooth would be imaged on that film, you can see how short it is. So that's foreshortening because of the angle of the film and the PID were not parallel to the tooth. If we could take that film and stand it upright and shoot perpendicular to the tooth in the film, now I've got an image of a tooth that's not distorted. But the root of that tooth is going to look all squatty on my film because of the angle that we see here. And there's more, that's on page 79, where they kind of show that whole distortion problem and what causes that and what that looks like. Okay, does anybody want to talk about any of these things that we've talked about? Distortion, magnification, sharpness. I feel like density and contrast, hopefully we've covered that and you guys feel pretty good about that.